Kia ora, Robert McLaughlin here. Welcome to week 6, lecture 1. Today we're going to look at a different kind of higher order linear differential equation, different from constant coefficient equations, which we've been mostly working with until now. It's called a Cauchy-Euler equation, and the distinguishing feature is the coefficients of each derivative term. So the coefficient of y double prime must be a constant times x squared. The coefficient of y prime must be just some constant times x. And the coefficient of y must be just a constant. And the reason this is a good equation to look at, not only does it come up in applications, as we'll see later on, but it has, whoa, what happened there? Has easily found explicit solutions. They're all powers of x. So instead of substituting some exponential and asking the question, which exponential will solve this equation, I say which power of x will solve this equation. So if y is x to the m, y prime is m x to the m minus 1. Y double prime is m minus 1 x to the m minus 2. Substitute into the equation, and I get ax squared times y double prime, well that's m minus 1 x to the m minus 2, plus bxy prime, well that is mx to the m minus 1, plus cy. And that has to be 0 for all x. And you notice that this term and this term will multiply together to give x to the m. This term and this term give x to the m. This term is x to the m. So I have a common factor of x to the m. am m minus 1 plus bm plus c equals 0. So the only way this can be 0 for all x is if m satisfies this equation, which is a quadratic equation for m, but it's a different quadratic equation than we got when we were doing the constant coefficient equations. There is a little problem here at x equals 0. If x equals 0, you can't cancel that term, but that's because the differential equation itself is singular at x equals 0. If you recall the existence and uniqueness theorem for higher order equations, you have a unique solution to an initial value problem in any interval where the leading coefficient, the coefficient of the highest derivative, is non-zero. So this equation will have unique solutions in an interval where x is positive, where x is negative, but not in some interval straddling 0. So we have to solve this equation and see what happens. It's the indicial equation. Now it's a quadratic, so there's some different cases to consider. Let's call the roots m1 and m2. Then I know from the general theory that the general solution is going to be y equals c1 x to the m1 plus c2 x to the m2. And that holds when I have distinct roots, namely m1 not equal to m2. So that's the easy case. What happens with the repeated root case? So I'll just do this through an example. Now the indicial equation, so y is going to be x to the m. The indicial equation is m minus 1 minus 3m plus 4 equals 0. Which if I expand out, I get m squared minus 4m plus 4 equal to 0. Factor it, m minus 2 squared equals 0. m equals 2 and 2. It's a repeated root. So that means I only really know one solution. y1 equals x squared. So how are we going to find a second solution? So there is a standard method for finding a second solution when you know one solution, and it's called the method of reduction of order. And what you do is you try y equals some function of x to be determined times the other solution that you found already. And when you substitute that in, you will get a lower order equation, a first order equation to solve for u. So let's see how that works in this case. I'm going to substitute y equals x squared times u of x, and the equation was, what was it again? Minus 3x plus 4. X squared y double prime minus 3xy prime plus 4y equals 0. I need to get my derivatives. So y prime is going to be first term times the derivative of the second term plus the derivative of the first term times the second term. Y double prime, use the product rule again. Here I get x squared u double prime plus the derivative of the first term times the second term. Now move on to the second one. First term times the derivative of the second term, I'm calling this the first term here, plus the derivative of the first term times the second term. Substitute in, and I get x squared times y double prime, well that is x squared u double prime plus 4x u prime plus 2u minus 3x y prime, which is x squared u prime plus 2xu, plus 4y, which is 4x squared u, whole thing equal to 0. Now that looks more complicated than what I started with, but if you look at it for a while and just look at the terms in u without the derivatives, I've got 2x squared times u minus 6x squared times u plus 4x squared times u. They all sum to 0, so I can cancel those out. What have I got left? Well, for the second derivative terms, I've just got x to the 4 u double prime. And for the first derivative terms, the u primes, I've got 4x cubed minus 3x cubed. That's just x cubed. Again, I can assume x is not equal to 0 because x equals 0 is a singular point. So I can divide both sides by x cubed and I get x u double prime plus u prime equal to 0. Now that is still a second order equation, but it's an easier one than I had before because I can make a substitution v equal to u prime, v prime equals u double prime, and I get xv prime plus v equal to 0. So that's the reduction of order step. And if you do this more generally, not in this example, but for any equation of this type, you will always be able to make the substitution and reduce a second order equation to a first order equation when you know one solution. How do I solve this one? Well, this one looks very easy. It's linear, it's first order, it's separable, so I could use various methods. Let's just do it like this. It's actually already a derivative. It's the derivative of x times v. Integrate both sides. xv must be a constant. V must be a constant over x. That means u prime. Now I know v, that means I know u prime must be c over x. And that means u must be the antiderivative of that. That is c log, I don't need the absolute value because I'm just assuming x is positive here, plus d. So I found the u. I'm running out of space, so y is equal to x squared times c log x plus d. Whoops. Now the dx squared, I already knew that was a solution, so the new one I get is x squared log x. And in fact, this is the general solution that I've got here. So that was an example, but this will always work. And the general rule is repeated roots m. The general solution is c1 x to the m plus c2 x to the m log x. So just as in the constant coefficient case, the repeated root case is special. Okay, so you can guess what's coming next. It's the complex roots case. Now I get that y is going to be x to the m, that is x to the alpha plus or minus I beta. So this looks a bit complicated because it's x to a power of a complex number. I need to rewrite that a little bit, so I'll rewrite that as e to the log x all to the power of alpha plus or minus I beta. Now I can use the power rule to multiply the powers, and I'll get e to the alpha plus or minus I beta times log x. And I can now expand out that power, and I'll get e to the alpha log x, e to the plus or minus I beta log x. And for the first term, I can just use undo the rule I just did and write that as x to the alpha. What about this term? That's e to a pure imaginary number. Recall Euler's formula, e to the I theta is cos theta plus I sine theta. So e to the I beta log x, I can write that as cos of beta log x plus or minus I sine beta log x. So why is that progress? I'm not quite there yet. I've rewritten it as more in terms of more familiar functions instead of x to a complex number, but I've still got complex solutions. Again, what you can do, just as we did for the constant coefficient equation, you can take these two solutions and add them, or you can subtract them, and you can get real solutions that way. So the two fundamental solutions are x to the alpha cos of beta log x, and y2 equals x to the alpha sine of beta log x. Now that's a fairly unusual function, but there it is. We've solved the equation. Okay, so we know how to solve these equations, and this example will be solving an initial value problem. I'm given the initial value of y and the initial value of y prime. So I first write down the indicial equation, so y is going to be x to the m. Indicial equation is m minus 1 plus m plus 1 equals 0. M squared minus m plus 1, sorry, m squared minus m plus 1 equals 0, so it's m squared plus 1 equals 0. M equals plus or minus I. So that means the general solution is y is equal to c1. So compared to the previous slide, alpha is 0 and beta is 1. So I get c1 cos of log x plus c2 times sine of log x. Okay, I've found the general solution. Now I need to fit the initial values, and I see that I'm going to need y prime as well. So I'll work that out first. Y prime is going to be, I'm going to be differentiating cos of log x. That's going to give me derivative of cos is minus sine, so I'll get minus c1 sine of log x times the derivative of log x, which is 1 over x. For the second term, I'm going to get c2 cos of log x times the derivative of log x, which is 1 over x. I notice the initial condition is given at x equals 1, so y of 1 must be equal to 1. Substitute in x equals 1. Well, log of 1 is 0, so that's a very convenient point to specify the initial value. I get c1 cos of 0 plus c2 sine of 0. Cos of 0 is 1, sine of 0 is 0. This is equal to c1, so c1 is 1. Y prime of 1 is supposed to be 2. This is going to be minus c1 sine of 0 times 1 plus c2 cos of 0 times 1, that is c2. So c1 is 1, c2 is 2. The solution to the initial value problem is cos of log x plus 2 sine of log x.